Welcome to Learning to Engineer. In this video, we are going to see some arithmetic circuits which are based on operational amplifiers. In the previous videos, we saw the equivalent circuit of an operational amplifier and some basic concepts involved with it. Now, let's jump into the arithmetic circuits that are based on this device. In calculators which were designed in early ages, this was the basic IC that was used to design the calculators. Now there are so many advanced digital versions of the calculators that are available which are not really using this concept. Here we will see how an OPAMP is used to design an adder, a subtractor and a gain multiplier circuit. Based on the similar concept, we can also design other devices like voltage controlled current source or voltage controlled voltage source, current controlled current source or current controlled voltage source. So all these types of controlled or the dependent voltage and current sources can be designed based on operational amplifiers. Now let us see these three applications and some problems that are involved with this in this video. Let's get started. This circuit performs the addition of three input voltages just like the name suggests. Okay, so the output of it will be the addition of these three voltages. How? Because we know that the gain of a negative feedback amplifier is minus RF divided by Rn. So this is the gain of this amplifier, and since we have three input voltages and by the virtual ground concept, here if the voltage applied is 0 volt, this is tracked by the negative terminal also, hence there will be a 0 volt. So all these three currents will get added over here and all of them pass into this output voltage. So this current, let me call this as IA. This IA will be I1 plus I2 plus I3, right? I1 plus I2 plus I3. Okay. So what is IA? The difference in voltage between these two ends divided by this resistor. What is IA? Since the direction is from here to here, so I am assuming that this is the higher potential and this is the lower potential. So IA will be 0 minus V out divided by RF, which is equal to I1. What is I1? The difference in voltage between these two divided by this resistor. What is I2? Difference in voltage between these 2 points divided by this resistor. Same for I3. So I1 will be V1 minus 0 volt. V1 minus 0 divided by R1, and same for I2, it will be V2 minus 0 divided by R2 plus V3 minus 0 divided by R3, and hence to find out the value of V out minus V out, this would be RF multiplied by the whole thing. So it is RF by R1 into V1 plus RF by R2 into V2 plus RF by R3 multiplied by V3. This is negative of V out. Positive of V out would be the minus of the addition of all these. This proves that the output voltage will be an addition of the input voltages times the gain. The RF, if it is designed to be equal to R1, it is a unity feedback, and hence it will be the inverted sum of V1, V2 and V3. When RF is equal to R1, R2 and R3, say for example, RF is equal to 100 kilo ohm, which is same as R1, R2, R3, this factor will get cancelled and this will be a adder circuit. Okay, so based on this concept, we will solve one problem. In this problem, RF is equal to 330 kilo ohm, R1 is equal to 33 kilo ohm, R2 is equal to 22 kilo ohm and R3 is equal to 12 kilo ohm. So for this configuration, what is the value of V out? It is just the substitution of the formula where V out will be the negative of Rf by R1 times V1 plus Rf by R2 times V2 plus Rf by R3 times V3. So if we substitute, this is actually a straightforward substitution. If we substitute, we will be getting the negative of 330k divided by 33k multiplied by 0.2 plus 330k divided by 22k into minus 0.5. Please note that this is a negative voltage. Okay, so what is the third term? I am just writing the third term below, plus 330k divided by 12k into 0.8 volt. So if we substitute, we will get the answer as minus 16.5 volt. Okay, this is a very this is just a basic problem. In the further videos, we will be solving problems which are a combination of one or more concepts. So in that case, these kind of ideas will be helpful for you to solve those problems. We also need to understand the concept of virtual ground better. So for that, I have just allocated a separate video for this. So do check that out before solving problems. Okay, so now we will see the subtractor circuit which is designed using an operational amplifier. It is just similar to our adder concept only. We are adding 3 voltages here. In the subtractor, what will happen? There will be 2 operational amplifiers that are cascaded to each other. When we supply voltage of, let us say, 0.1 in the input, and let us say the gain is 1, unity gain. Okay, so what will be the output? Output will be minus 1, right? So if we want to add 2 voltages, let us say VA minus VB. So the negative voltage VB has to be given in the first stage, and the positive input will be given in the second stage of the amplifier, where the combined output will be VA plus minus VB, because we are inverting VB. Okay, I will draw the circuit of subtractor. Okay, this is a subtractor circuit using operational amplifier. Okay, so the first input will be given here and the positive input will be grounded, and this will be tied to one more inverting amplifier where it has another input of VB, and the positive terminal will be connected to the ground terminal. This is the feedback resistor and this will be the output. Okay, let me just call this as R1, R2 and R3 for time being. Okay, and this is RF or maybe RF1. Okay, so the output of this will be the subtraction of VB minus VA. Okay, let us see how it works. This is one inverting operational amplifier. The output at this terminal will be minus RF1 by R1 times the input VA. The output at this stage, let us call it as VA. Okay, VA is this input, right? So let us call this to be V small a. Okay, so V small a will be the negative of RF1 divided by R1 multiplied by VA. Okay, so when you consider the second operational amplifier, this will be an addition of 2 inputs, which is VA, V small a plus V capital B. Okay, so the output will be the inversion of addition of both of them, right? So what is V out? V out is going to be the negative of VA times RF divided by R2 plus VB into RF2. I'm sorry, RF2 divided by R3. Okay, this is based on the adders concept. Now, what is the value of VA? It is already a negative value. So, this V out is going to be the negative of minus RF1 divided by R1 multiplied by V capital A, which is the applied input at this stage. Okay, this into RF2 divided by R2 plus RF2 by R3 into VB. Okay, so what is the V out? Let us take the multiplication factor inside. We will be getting VA multiplied by the first stage gain into the second stage gain minus VB into the second stage gain. If both of them have a unity gain, then it will be VA minus VB, which is a subtractor circuit. By tactfully tying one op-amp's output to the other op-amp, we are making it as an inverting amplifier. I have few questions for you here. Why are we grounding the positive terminal? Why are we making it an inverting op-amp? Because we want a term minus VB. We want to invert one particular input so that we can subtract. Okay. So to invert, we are connecting a inverting amplifier so that the output will be minus of RF by R1. When both these resistors are same, RF and R1, the output will be the inversion of the input. So to purposefully make this as invert, I am connecting it to one more inverting amplifier. Minus of minus will be becoming plus here, and we are subtracting both the voltages VA and VB. Once we start solving problems over these concepts, we will be able to understand these better. Okay, we can just have the value of RF, R1, and we can just solve for V out. RF1, let us take it to be 330K. R1, let us have it as 33 kilo ohm. R2, let us have it as 47 kilo ohm. And R3 is also same, it is 47 kilo ohm. By tactfully manipulating the value of RF and R1, we can adjust the gain. We will see that concept here. Okay. In the second stage, if you observe, RF by R1 will be minus 10. It is minus 10 for this input also. So for this, the gain is minus 10. For this also, the gain is minus 10. Do you get the point? See, it is, let us say this is VA and this is VB, right? So RF2 by R2 is 10 here, because this is RF2, this is R2. 470K divided by 47K is 10. So this times 10 and this times 10. It is 330K divided by 30, the gain is 10. Okay, so by carefully designing a circuit in this way, we can perform arithmetic calculations by using operational amplifiers. Okay, so in the same manner, let us say for example, you are using a sensor like thermocouple, RTD or some other sensor to detect a temperature or a pressure or whatever be the process parameter. You are designing the circuit to amplify this voltage and to give a measurable reading in a, let us say, in any kind of a meter. Okay, so you need a decent amount of amplification over there. The output from the sensor, it will be typically of picovolts or microvolts. Okay, let us say for example, you are getting a temperature temperature output of, let us say, 100 degrees Celsius. It will be in a voltage of, let us say, 1 or 2 microvolts, and this 1 or 2 microvolts has to be amplified by by this system in order to be sent to a readout where you can see the reading. Okay, so for that kind of amplification we use gain multipliers. This microvolts will be multiplied by the amplification factor of the op-amp to get few millivolts, and that will be multiplied by another op-amp to get a gain factor of 1 or 2 volts. In another stage, it will be multiplied by 10 or 20 or whatsoever be the gain of that amplifier to get a large amount of voltage to be sent into the readout. If you are sending few microvolts, the circuit will not be able to accept that sensor's output to display it as just as a digital reading. Even for that, to sense the sensor's output, it needs to be in a measurable amount of threshold. So we definitely need gain multiplying amplifiers. One single amplifier we cannot put it, let us say 2 into 10 power 12, you cannot multiply. Okay, because if the sensor's input at one stage, let us say for example, it is 0.1 into 10 to the power minus 12 volt. Okay, so for that to be measured by a readout, you need this output to be 1 to 5 volt at least. Let us say for example, how will you do a multiplication? You have to multiply it by at least 10 power 13 so that you can get 1 volt. Okay, so 10 power 13 should be the gain of that amplifier. Ideally, amplifiers have infinite gain, But practically the circuits are not like that. You can find out the open loop gain of those circuits in OPAMP. In the OPAMP's data sheet, you can use the data sheet of that OPAMP to find out the open loop gain. So the output will be the open loop gain times input voltage. So this high value cannot be achieved by one single amplifier. So they cascade amplifiers together. This is called as a gain multiplier. I'll just do it in a block diagram fashion. Okay. Let us say the A1 is one amplifier, A2 is another amplifier, and this is V out. And let us say, for example, you are connecting your RTD or thermocouple to this, and the range is, let us say, for example, 0.1 into 10 power minus 12 volt. Okay, the gain of it can be 10 power 5. The gain of this can be 10 power 5. So the overall gain will be 10 power 5 times 10 power 5. Okay, so this is gain multiplication. So this output will be, let us call this as V1, voltage output at stage 1. Okay, this will be minus RF by Rin multiplied by the input of 0.1 into 10 power 12 minus 12 volt. And here if you give this to the second stage, the output V2 will be minus RF2 divided by Rin2 multiplied by 0.1 into 10 to the power minus 12 into Rf1 divided by Rin1. So by this process, we are multiplying the gain to this input and hence getting a higher value of output. This is called as a gain multiplier. So there are similar applications of operational amplifier based on this amplification concept. Okay. There is another concept also like a comparator or Schmidt trigger where positive feedback is used. In all this amplification process, negative feedback is used. Okay, so in Schmidt trigger circuit, in astable multivibrators, in comparators, in all these concepts, we need to understand the positive feedback idea of an op-amp to proceed further. So I recommend you to check out this video where I have talked about the virtual ground concept of op-amp, and then proceed with the video where I have explained the positive feedback concept in order to understand this the application of Schmidt trigger and comparator concepts also. Okay, so thanks for watching. Do let me know your thoughts in the comment section, or you can write to learningtoengineer@gmail.com. Thank you.